Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Sean Welch, your host. I am the host and producer at Data Science Central. I'd like to start our event off today by thanking Gurobi for sponsoring today's event. Gurobi is a longtime supporter of the Data Science Central community, and we are honored to have them sponsoring our event today. Today's webinar is entitled, How to Create Mathematical Optimization Models with Python, to be presented by Gurobi. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be 1 hour long, and we have one presenter who I'll introduce in just a minute. There will be a 10 to 15 minute Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Juan Orozco Guzman. Before joining Gurobi Optimization, Juan spent several years in the IT industry, performing roles in R&D, business intelligence, and data science. He has also taught undergraduate courses about statistical process control and mathematical optimization in the Industrial Engineering Department at ITESM, Campus Guadalajara. Juan earned an MSc in Statistics and Operational Research at the University of Edinburgh with distinction. His main interests are in optimization, machine learning, and deep learning. Thanks for being with us today, Juan. We're looking forward to your presentation. With mathematical optimization, companies can capture the key features of their business problems in an optimization model and can generate optimal solutions, which are used as the basis to make optimal decisions. Data scientists with some basic mathematical programming skills can easily learn how to build, implement, and maintain mathematical optimization applications. The Gurobi Python API borrows ideas from modeling languages, enabling users to deploy and solve mathematical optimization models with scripts that are easy to write, read, and maintain. Such modules can even be embedded in decision support systems for production-ready applications. In today's Data Science Central webinar, we will discuss the motivation for using Python in mathematical optimization applications, help you understand the importance of parameterizing a mathematical optimization model, and review some of the best practices for deploying mathematical optimization models in Python. Juan, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thank you very much, Sean. So in our previous webinar, we focused on how we can translate a business problem into a mathematical optimization model. But in today's webinar, we are going to focus on how we can translate those mathematical expressions into a script that can be read by a machine. So here is the agenda. First, I will give an introduction on mathematical optimization. Then I will present the main elements and the supportive elements of a mathematical optimization model. Then I will give some motivation on how, for the reason of using Python instead of other modeling languages. Then I will present the main objects that are in the Gurobi Python interface, so that later we can discuss some issues, for example, model sparsity, and some other best practices when building mathematical optimization models. And finally, we will wrap up this webinar with some final thoughts. So without further ado, let's begin. So if you recall from our previous webinar, we can trace back the origins of mathematical optimization back to the invention of linear programming shortly after the World War II by George Danzig. And basically, mathematical optimization is a declarative approach where the modeler has to state all of the properties associated with a solution. And not only that, but he also needs to define a criterion to guide the search. And this is in contrast to other algorithmic approaches where the modeler has to specify all of the necessary steps to build and test a solution. And a clear example of this is when we have to implement heuristics that uses rules of thumb that we gain from our experience, right? So if you ever wondered about the meaning of our logo, well, basically that's the geometric representation of the set of all admissible solutions. And in this case, each axis represents a possible course of action, and then each facet of this figure is associated with a constraint, right? Because no system is unlimited. We may have limited resources on the amount of raw materials, on we may have budget constraints, time constraints, the number of machine hours that we can use, or man hours that we can use, right? Now let's present the elements of a mathematical optimization model. And before we do this, I want to introduce the assignment problem, which is one of the most renowned problems in optimization, and which we also presented in our previous webinar, right? So basically in this problem, we have two different sets, right? We have one set of resources, which can be people, and we have another set for the jobs that we can or that we want to be performed, right? And in this problem, basically we want to assign at most one person to each job. And similarly, we want to assign at most one job to each person, right? And if you imagine that it's possible for us to compute a matching score that takes a value between 0 and 100, and this value represents how proficient a person is when performing a job, then we may say that we want to maximize the total matching score from the assignments that we make, right? So basically, to solve this problem, we can define a set of decision variables for each combination of person and jobs, right? And we can associate a binary decision variable that takes on the value of 1 if person A is assigned to job J and 0 otherwise. And I like to think of mathematics as a universal language, because basically these words can be our dictionary with which we can convey ideas, right? So if we focus our attention on the right part of this slide, and then going from bottom up, you can see that on the last mathematical expression, we are creating a binary decision variable for the Cartesian product between the set of persons and the set of jobs. Here, the set I denotes the set of persons, and the set J denotes the set of jobs, right? On the next mathematical expression, we can see that we deploy a constraint for each person in the set of persons. And then we said that we need to focus our attention on all of the jobs that can be assigned to that person. And then we say that the summation of the corresponding decision variables must be less than or equal to 1. And likewise, on the next mathematical expression, we see that we need to deploy a constraint for each job in the set of jobs. And then we say that we need to focus our attention on the set of people that can be assigned to that job. And then we need to ensure that the summation of the associated decision variables is less than or equal to 1, right? And finally, on the next mathematical expression, this is where we define the objective function. And basically, we're saying that we want to maximize a function. And this function is basically the sum of the matching scores. Notice that each term in this summation is basically the multiplication between the matching score and the corresponding decision variable, right? So for example, if we decide to assign Juan to the job webinar, then that variable will take on the value of 1, and then this multiplication or this product will be equal to the matching score, right? Whereas if we do not assign Juan to webinar, then that variable will take on the value of 0, so that this whole term is rendered to 0, right? And this is where the beauty of mathematics happen, because basically we can expose the inner structure of a problem, right? And that structure can be shared between problems that apparently have nothing to do between them, right? So for example, there's another type of problem called the p-median problem that has applications not only on logistics, but also on machine learning when we want to cluster a group of objects. So now that we can actually use this problem, let's introduce the main elements of a model, right? And the first ones are the decision variables, right? And remember that these variables represent decisions we can make or activities we can do, right? And these variables can be either continuous or real valued, but they can also be binary or general integer variables, right? The next main ingredient is the objective function, right? And remember that a specific combination of activities is what defines the performance of the system, right? And this performance is represented by this objective function. Then you may remember this from your calculus courses, but when we are optimizing this criterion, what we want is to follow the gradient of this function. Why? Because basically the gradient gives us the direction of maximum improvement. The third main ingredient of a model are the constraints. And they are very important because not all combinations of activities are valid, right? And we can think of a constraint that defines a plane in n dimensions, and then there is a wrong side from that plane, and there is a correct side from that plane, right? Then for a combination of activities to be feasible, basically we need to satisfy all constraints simultaneously. And geometrically, what this means is that the point that represents the combination of activities must lie in the intersection of all valid health spaces, right? So basically, we need to be inside of our of the Gurobi logo, right? And while these are the main ingredients of a model, we also have some other ingredients that help us parameterize the models, right? And the first ones are the data coefficients. And in this case, the matching score is a data coefficient, but also the right-hand sides of the constraints. In the assignment problem, they are all equal to 1, but in general, the right-hand side can take on any number. And you may not notice this, but in each constraint, we're also multiplying an implicit 1 by the decision variables. These numbers are called the technical coefficients. And these numbers, in conjunction with the right-hand sides, is what define the location of the plane of the associated constraint. The next element is a set, right? And basically they help us define how constraints are deployed and which elements needs to be considered in a summation, right? So basically we're using the sets to deploy all of the instances of the constraints that we need. And not only that, we also use those to know which decision variables we need to sum. Then we also have subscripts, and they are very important because they let us access to a specific decision variable or data coefficient. Because remember that we have many decision variables, one for each combination, in this case, between a person and a job, right? So if you want to access the value of the decision variable associated to Juan and webinar, then you can subscript the variable vector to retrieve that specific value. Then we also have arithmetic operators. And in this case, we only have multiplication in the objective function, right? As we are multiplying the matching score by the decision variables. But notice that we can also use addition, right? And when I say multiplication and addition, obviously I'm also referring to division and subtraction, right? Then we have constraint operators. And these operators are the ones that define which side of the plane defined by the constraint is the correct one and which one is the wrong one, right? So in the assignment problem, we only have less than or equal to, but in general, we can also see greater than or equal to, or even equality operators, right? Just bear in mind that in linear programming, it is not admissible to have strict inequalities, right? So it's not possible to just have greater than or less than, okay? Then we also have the for all operator, and this operator enables us to define a set of constraints which will then be deployed, right? And this way, we can focus on generic ideas without worrying about the details of implementation, right? Because we may have hundreds or thousands of jobs. And using this operator, we just need to state the fact that at most we can assign one person to each job. So we don't need to instantiate all of these constraints, right? The modeling language will be in charge of doing that. And finally, we also have the aggregate sum operator. And this is very useful to logically group the contribution of a subset of decision variables. And note that the aggregation sum is represented by the big sigma notation. So to summarize, we have seen that there are three main ingredients in a model. We have decision variables, we have an objective function, and we have constraint sets. But we also have some other elements. We have data coefficients, we have sets and subscripts, and we have different kind of operators, such as arithmetic operators, constraint operators, the for all operator, and the aggregate sum operator. So now let's talk a little bit about the motivation for using Python, because you may know that out there are many modeling languages. So why would we want to use Python as an alternative to those languages, right? They perform a very important job because modeling languages help us translate a mathematical formulation into a machine-readable format, right? And this is important because real-life problems may involve thousands or even millions of constraints and variables, and it is impossible to generate by hand each constraint and each variable individually. So just as we will not solve the problem by hand, we don't need to specify each mathematical expression by hand. Some desired traits in modeling languages are the following. So the code needs to be easy to write and maintain, and if possible, also easy to read. These languages need to cover all solver and programming needs, and they should offer low overhead when deploying the model as compared with the solver alone. So why using Python and not different programming languages? Basically because it is fast and powerful, but it is also easy to learn, use, and read. Then it is also extendable with a vast library of pre-written modules about the statistics, graphical user interfaces, web services, data connections. So you know that in data science, in our day-to-day operations, we use different modules such as NumPy, SciPy, Pandas, scikit-learn, or Matplotlib, right? Then it's also in the top 3 most popular programming languages according to the TIOBE index. And for this reason, we have a large community of active users. And this is especially true for data science, because I dare to say that Python is the most used language in our community. And lastly, but not least, it is also free and open source with licenses that are business friendly. So we can use, we can build decision support systems for our organizations. And while you can edit a Python script even using a simple text editor or using programming editors that enables syntax highlighting or autocompletion, or even IDEs, I would like to focus our attention on Jupyter notebooks. Basically because they are also extensively used in data science. So basically, Jupyter notebooks are web applications to create and share documents that contain not only live code, but also explanatory text, mathematical equations, and visualizations. And these traits are excellent for reproducible research, because usually what we want is that our peers are able to replicate the results of our analysis, right? You may have felt the pain when we want to reproduce the results of an academic paper, right? So with these Jupyter notebooks, this is an easier task. And the good thing about Jupyter notebooks is that they are also free software with an active community. So if you want to learn more about this, you can follow that web page. So now let's talk about the objects that are provided by our interface. The first one, and you will notice that some of them are directly associated to the elements that I previously explained. The first one that I want to talk about is the model object. And this is associated to, obviously, an optimization model. Then we also have the object called bar. And this corresponds to a single decision variable. We also have the object called constr that is associated for a functional constraint. And then our interface has overloaded some operators, such as the arithmetic operators and the constraint operators. Then our interface provides an aggregate sum operator called quicksum, and we will see this later. And not only that, but also our interface provides additional data structures called tuple lists and multidicts. And basically, this is everything you need to know to start modeling with this interface. Basically, because Python provides the rest. Python provides functions to read data, to print out or write solutions, and also, of course, to define control and looping statements. So now let's see a very simple Python example where we solve a very simple model, right? In the first two lines, basically, we are importing our module. On the next line, we are instantiating a model object that is called MIP1 and is stored in the variable model. Then we create three different decision variables, x, y, and z, using the add_var method in singular, right? And notice that we are telling Gurobi that these variables are binary. On the next line, we are defining the objective function for the model by using the setObjective method. And in this case, the expression is x plus y plus 2 times z. And we say that the sense of the optimization is to maximize this function. So we can either maximize or minimize. But in this case, we're maximizing. On the next two lines, we are adding a couple of functional constraints using the add_constr method, again in singular. And in this case, the constraints are as follows. The first one is x plus 2 times y plus 3 times z, and that must be less than or equal to 4. And the next one is basically x plus y, and that one must be greater than or equal to 1. And finally, the last line is where we actually solve the model by calling the optimize method. So, of course, this is a very simple model that we can write by typing each command. But of course, if you have thousands or millions of variables and constraints, you need to be clever about how to deploy such models. And this is where using different data structures come in handy, right? So Python provides some data structures that are well suited for indexing and subscripting, such as lists, dictionaries, and tuples. And as I already told you, Gurobi also provides tuple lists and multidicts. So let's take a look at each of these. The first data structure that I want to talk about are tuples. And tuples are a fixed compound grouping. So imagine that we have a transportation network where we are producing goods of one type, and we want to transport these goods from our factories to our customers, right? So on that transportation network, we may have the possibility of sending goods from our factory in Chicago to our factory to our customer based in New York City. And that can be expressed by using a tuple. The important thing of tuples is to remember that they cannot be modified once they have been created. And this is because they are immutable objects in Python. But also remember that they are ideal for representing multidimensional subscripts. So imagine again that in our transportation network, we are not only producing one type of goods, but several types of products, right? So if we want to look at the possibilities of how we can send products one from our factories to our customers, then one possibility could be shipping those from Chicago to New York City. And then, of course, we're referring to product number one. But we can have similar tuples for other product types. The next data structure are lists. And lists are basically order groups. So imagine that for some reason you're interested into looking at all of the nodes in our transportation network. And in this case, we have Chicago, New York City, Atlanta, and Miami. Lists are different from tuples in that they can be modified. So we can add elements to the list, we can delete elements from the list, and we can even sort elements within that list. Unlike mathematical sets, a list can have repeated elements. So if you want to be super secure that you are not repeating elements, then you can use a different data structure called set in Python. But usually with lists are good enough for our implementations. The next data structure are the dictionaries. And basically, a dictionary is a mapping from keys to values, right? So imagine that there is a cost associated for transporting one unit of product from our factory to our customer, right? So imagine that transporting from Chicago to New York City has a cost of 100, while the cost of transporting one unit of product from Atlanta to New York City has a cost of 150. Basically because Atlanta is farther away than Chicago, right? So the important thing to remember here is that keys can be basic values, such as integers or strings, but they can also be tuples. And they are ideal for representing index data. So imagine that in this transportation network, we not only have data about the cost, transportation cost, but also about the demand from our customers, and then information about the capacity in our facilities, or even consumption rates when producing these goods, right? So to produce one unit of final product, we may need different types of raw materials at different rates, right? This can all be expressed using dictionaries. Then we have some data structures provided by our interface. The first one are the tuple lists. And basically, this is Gurobi's extension of lists. And they are very efficient for storing a list of tuples. So basically, imagine that we can store in the variable args all of the possible routes to transport our product from our factories to our customers, right? And the important thing about tuple lists is that they have a very special method called select that help us find matching subsets. So basically, with this method, we can query on the tuple list args to retrieve all of the tuples where the first element is related to Chicago, right? And notice that we are using a wildcard, the asterisk, saying that we do not care about the content in the second element. And then if we run this function, basically we are gonna get back a list with two tuples, right? And these two tuples are the ones that have Chicago as the first element, right? We're gonna be using this method extensively because of the efficient indexing capabilities of this method. And the final data structure that I want to talk about are multidicts. And these are convenience functions to initialize dictionaries and their indices in just one statement, right? So basically, the argument for this function is a vanilla dictionary where we have the shared keys, in this case, the cities, and then the values are lists of the same length, right? And notice how the first output is the variable cities, and this is basically a tuple list. And the remaining outputs are, again, vanilla dictionaries that have the keys in common. So for example, the dictionary supply will have Atlanta, the key value per Atlanta 100, Chicago 150, New York 20. While the dictionary demand will have the key value pairs Atlanta 20, Chicago 50, New York City 300, so on and so forth, right? So just remember that the first object returned by this function is a tuple list. So of course you can use the select method. So now let's see a different example called the diet model, but this time let us take a look at this using Jupyter notebooks. So let me share my screen. So in this problem, we can think of us as nutritionists that want to minimize the cost of purchasing food while still satisfying the nutrition requirements of our patients, right? Don't pay too much attention on the first block of code, because we're basically defining a helper function to print the optimal solution of our model. But on the next block of code, notice that in the first few lines, we are again importing our Gurobi module. Then we are using the multidict function to specify the set of nutrient categories, but also the dictionaries for the minimum nutrition requirements and the maximum nutrition requirements, right? Then we use again the multidict function, but this time to set the set of foods that we can buy, and also the cost that each type of food costs, right? And finally, we are specifying a vanilla dictionary where the keys are all possible combinations between the set of foods and the set of nutrients, right? So basically, we're defining the Cartesian product between these two sets. And in this dictionary, we are storing the nutrition values for these combinations. So for example, a hamburger contributes with 410 calories, whereas chicken contributes to 420 calories. Then on the next line of code, we are instantiating a new model object, and then we are using the add_vars method. Notice that this method is in plural, so it is working on the tuple list of foods. Of course, we can also use the add_var method in singular, but in order to do that, we need to embed it into a looping construct. Then, after creating our decision variables, which conform our dictionary to convey our ideas or our constraints, we set the objective function by using the setObjective method. And with this function, we're basically defining the inner product or the dot product between the variable vector and the vector that contains the cost for these foods. And then we say that we want to minimize that dot product. In other words, what we want is to minimize the total cost of our nutrition plan. Then, of course, we can also use generator expressions to express this total cost. But in this case, we need to use the quick sum function, right? And then we need to specify the total cost for each type of food, right? So notice how we are multiplying the cost per unit for each type of food by the number of items that we buy from each food category. And then we are summing over all foods in our tuple list foods. Lastly, we need to also define the functional constraints. And basically, these constraints will ensure that our nutrition plan are between the minimum and the maximum nutrition requirements. So for this, we're going to use the add_const method, again in plural, right? And basically, we are going to deploy one constraint for each nutrient in the tuple list categories. Then we are going to compute the contribution to one specific nutrient category for all of the units of food that we buy for a specific type of food, right? So we are multiplying the nutrition value for each unit of food times the number of items that we buy of that specific food, and then we sum over these products over the set of foods, right? And we say that that total nutrition value should be at least the minimum nutrition requirement. And then on the other set of constraints, we're saying that that same expression, which represents the total nutrition contribution, that sum needs to be less than or equal to the maximum nutrition requirements. And finally, now that we have the objective function, the constraint sets, and the decision variables, which are the main ingredients for a model, we can call the optimize method to actually solve this model. And then, of course, we can print out the solution. So if I run this, we can see that in the optimum, we need to buy 0.60 hamburgers, 6.97 units of milk, and 2.59 units of ice cream. So I don't think our moms will be proud about this plan. But this plan has an optimum cost of $11.83. So you can see that it is very simple to specify a mathematical model using the Gurobi Python API. So let me stop sharing my screen and go back to the slide deck. So now let's talk about sparsity and some best practices. And by sparsity, I mean model sparsity and not a sparsity on matrix sparsity, because matrix sparsity is already handled by our solver, right? And I want to talk about the sparsity by presenting a couple of mistakes that we see are very frequent. So for this one, let's consider the assignment of workers to shifts, where the workers need to indicate their availability by shifts, so that you cannot assign a worker to some of them, right? So in this case, we are defining a tuple list with all of the valid assignments, possible assignments, right? Then we're defining a Python dictionary where we are going to store the decision variables. And note how we are looking at every possible combination of workers and shifts. And then for each of these combinations, we are adding a decision variable. But then if that combination is not in the tuple list availability, we are changing the upper bound of that variable to be equal to 0. And as the lower bound by default is also 0, basically with this, we're saying that those variables need to be exactly equal to 0. So you can see here that this is an overhead for both modeling and solving, because we are looking at the Cartesian products between the worker and the shifts sets. So the correct way of doing this is to just use the tuple list to store all valid combinations and use a Python dictionary to store the decision variables. But instead of looking at the Cartesian product, we can traverse directly the elements or the tuples, the tuple elements in that tuple list, so that we create a decision variable only for valid combinations. So this is much better. And the next mistake that we usually see is when users are creating functional constraints. So imagine that we have a specific requirements on the number of workers that need to be present on a specific shift. So of course, to express that to Python, we need to use the add constraint method in plural. And then, of course, we need to create one such constraint for each shift in the tuple list shifts. But notice that on the left-hand side, we are saying the actual requirement on the number of workers, and that needs to be equal to the assignment of people on that shift. And to do that, we're using the quick sum function, and we are saying that we want to sum the variables x of WS for each worker in the set of workers, only if that the tuple WS is in the set of availability, right? This is not ideal because basically we are iterating over all workers. And then we are deciding on whether or not the associated variables should be included in the summation or not, right? So the correct way of doing this is to just use the add constraint method and set the left-hand side to the number of required people. But then the generator expression used within the quick sum function needs to be as follows. Basically, we're saying that we want to add the decision variables for the tuples that are in the tuple list returned by the select method. And notice here how we are querying all of the tuples where the second element has the value of the shift that corresponds to the constraint that we are building. So notice how with this option, we are iterating only over the valid combinations of workers and shifts, rather than traversing the whole tuple list for workers. So how to exploit sparsity is by using tuple list to specify valid combination, and then by using variables and data as dictionaries that are indexed by these tuple lists, and of course, by using the select method to efficiently iterate over valid combinations. So some other best practices when building mathematical optimization models in Python, besides sparsity, is using list comprehension and generator expressions, just as we did within the quick sum function. And of course, another best practice is to use the quick sum function provided by our interface, which is a direct replacement of the a Python function called sum. And why is this? It's basically because quicksum is specifically designed to be more efficient when creating sums in optimization models. So I am not saying that quicksum in general is better than sum. It is just that for optimization applications, it is much better. And another best practice is to separate the logic for model deployment with the data that we're going to use to instantiate the model. And of course, whenever possible, we should use external sources of data, such as text files, spreadsheets, or even databases. So you can take a look in our website and look for these scripts. For example, the diet model.py is a module where we specify the logic for model deployment for the diet model that we just saw. Then the script diet2.py is a Python script where we hard-coded the data that we need in a separate script, which within which we later make a call to a function that is defined in diet model.py. And then the other script is diet3. And in that case, instead of having the data hard-coded, we have Python read the data from a SQLite database. So now let's give some final thoughts. We have seen that there is some commonality between modeling languages and our interface, in that we have a concise and readable syntax for building models, and we have interactive model objects so that we can manipulate the data within it. We also have efficient handling of dense and sparse data, and there are convenient connections to external data sources, like the ones I just explained. But there are also some differences between the modeling languages and the Gurobi Python interface. For example, in modeling languages, we have a specialized language for math programming, so that we have a syntax and primitives that are specifically designed for optimization. And not only that, but they have also implemented some of the best practices directly into the language. And because of this, the error handling is better because it is specifically tailored for optimization. Whereas the Gurobi Python interface is part of a general purpose language, and in that we offer greater flexibility because Python is designed with deployment in mind. So as you know, we can build very complex programs in just one language, and we can integrate very easily with databases, web servers, and so on, right? And of course, our interface covers all features that we need for our solver. But the best part is that by using Python, you have access to a very large user community, right? Because some say that a very important trait of a good programmer is that they are good at making searches on Google. So of course, you can refer to Stack Overflow of these types of platforms where you can get the answer to your problems. So to wrap up, here you have some resources. So for example, you can visit our website, gurobi.com, and then select I am a data scientist, and browse through our resources pages for beginners, intermediate users, and advanced users. We also have some tutorials about mathematical modeling. We also have some interactive demos and some Jupyter notebooks where we provide some examples, right? So let me quickly share my screen to show where you can find these resources. So this is our web page. So on the resources, you can go to code examples, and there you will find the Jupyter Notebooks examples that I just mentioned, but also some scripts or source code in several languages. Then you can also look for our demos under this section, right? We have 7 of them right now. And finally, you can also take a look at the tutorials that I mentioned. So if you want an evaluation license that is good for 30 days, you can visit that web page over there. And if you ever need help leveraging optimization for your business, you can contact us at info@gurobi.com. So this marks the end of our presentation. Thank you very much. And with this, I hand over the mic back to Sean. Thank you, Sean.
Juan, thanks for that excellent presentation. And we'll get started with today's Q&A session, and I want to thank the audience for their participation. We've had a great many questions that have come in during the presentation, and we'll do our best to get through all of them in the time remaining. And during this Q&A session, I'll leave up this screen with contact information for Juan if you'd like to contact him for a copy of the slide deck following today's webinar. All right, let's get started. Juan, does Gurobi impose a limit on the number of variables or constraints?
Not per se, but ultimately the size of the problems that can be solved depends on the processing power and the memory capacity of the machine that you are using to solve those models. So in practice, yeah, there are limits. But just to note that our solver does not impose any limit on the number of variables or constraints.
Okay, thank you for clarifying, Juan. The next question is, does Gurobi allow to specify optimization models via matrix notation?
Sure, this is a very good question. And with previous versions, this was not possible, at least in Python. But with version 9, we have introduced a matrix API for Python, right? That is actually very, very inexpensive to use because the deployment of the model happens on a lower level, that it's on C. It does not happen on Python itself. So yeah, we now are able to use a matrix API.
Okay, great. The next question is, can I use optimization to solve machine learning problems?
This is a wonderful question. Yes, indeed, because machine learning often relies on optimization techniques to learn the parameters of a model. But not only that, optimization can also be benefit from machine learning. Because, for example, our solvers have some hyperparameters that can be tuned for specific model instances. So you can imagine that we can use either supervised learning or even reinforcement learning to find the right set of parameter settings. So yeah, in that sense, optimization helps machine learning, and machine learning also helps optimization.
Okay, wonderful. Next question is, can logical constraints such as if-then or XOR be modeled with the Gurobi Python interface?
Yes, we can actually combine predicate logic with arithmetic so that we can get the benefits from expert systems. And Gurobi even has some general constraints to help you model some types of them. So for example, we have general constraints for capturing the absolute value on a variable, or for taking the maximum value over a set of variables, or the minimum value as well. And also we can generate and or conditions with these general constraints. But of course, you can also do this on your own without needing to resort to these general constraints.
Okay. Next question is, can Gurobi handle nonlinear models?
Oh, this is a very good question. Yes, we can also solve some nonlinear problems, such as quadratic programs or quadratically constrained quadratic programs, or even some types of nonlinear programs, such as the bilinear programming, right? In general, that's not the case for the non-convex problems, but specifically for bilinear programs, it is possible. But also notice that Gurobi lets you use piecewise linear approximations for single variable functions. And when you are using these linear approximations, then we can have any kind of constraint or function, sorry.
Okay, thank you for clarifying. And Juan, does Gurobi have API that connect to other languages?
Yes, we also have APIs for Java, for C, C++, C#, MATLAB, and also for R, for those of these data scientists that are more used to this language.
Okay, great. So Juan, thank you. Some great answers to some very, very good questions. And for those of you that asked questions that weren't answered today, we will be sending all unanswered questions to Juan and the Gurobi team so that they can follow up with you after today's webinar. I have just a few quick announcements. Please mark your calendars for April 30th, 2020, and our next DSC webinar. Graph algorithms combined with ML are saving the world. Also, today's taping will be available for on-demand viewing later today and can be found on the homepage of the Data Science Central webinar homepage in the webinar tab located at the top of the page. And past webinars are available on demand at datasciencecentral.com. If you haven't had the opportunity to view them, I encourage you to take a look. They provide very useful insight into a wide variety of topics of interest to our data science community. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to Gurobi for their sponsorship, as well as to our speaker today, Juan Orozco Guzman, for his insight into today's topic. My name is Sean Welch, and I'm very pleased to have been your host for today's event. I look forward to seeing you all again on April 30th, 2020. Have a great day.